Let's use this example of the rope swing to put into practice the law of conservation of energy. In a previous video lesson, we derived this equation that expresses the law of conservation of energy based on the work kinetic energy theorem. We say if we take all the mechanical energy initially in some system, then it equals the sum of all the final mechanical energy. In more detail, if we add the initial gravitational potential energy plus initial elastic potential energy plus initial kinetic energy, it equals final gravitational potential energy plus final elastic potential energy plus final kinetic energy. Or better yet, we can say mgh initial plus 1/2 kx initial squared plus 1/2 m v initial squared equals mgh plus 1/2 kx squared plus 1/2 mv squared. Now, in the problem of a rope swing, somebody just grabs hold of the rope and steps off a ledge. We'll say that the rope has a length of L. We can assign a numerical value to it. Maybe say this is a rope that's 6 meters in length. And how about we give a value for the mass of this person? How about 50 kilograms? Okay, well, first of all, if we're going to measure heights, we need some kind of a reference system. So you might be tempted to say that the level of the water that they swing over is h equals 0. But in that case, then you'd have both some initial height and some final height to deal with in the problem. So I think it's a good idea to label the starting position and the final position as some point A and point B in your sketch. So if you want to make it so that there's no potential energy when the object reaches point B, then you're welcome to assign h equals 0 at any reference level you want to. Okay, so if this is the case, there's clearly no spring involved. So we don't have to calculate any initial or final elastic potential energies. Because the person starts from rest as they just gently step off this ledge, there's no initial kinetic energy. And because we set h equals 0 at the final position, then there's no final gravitational potential energy. So the law of conservation in this case reduces quite a bit. We just get mgh initial is equal to 1/2 m v final squared. So I'm not sure it matters too much that we know the mass of the person is 50 kilograms. That ends up canceling out. And if we want to know their speed as they swing through the low point of the swing, all we need to do is multiply both sides of the equation by 2, take the square root, and we have v equals the square root of 2gh. Interesting, that's the same equation we would get if we were to use kinematics to figure out how fast something hits the ground when dropped from a given height. And this brings us back to the idea that work done by gravity is path independent. It doesn't matter if the path toward a lower elevation is a straight line or part of a circular arc. In the end, the final speed that's developed is independent of the path taken, provided there are no non-conservative forces acting in the process. Okay, well, we don't really have a great expression for h in this problem, do we? So we have to go back to our diagram and consider it a little more carefully. How about we draw an elevation line that represents the initial height, just going straight across, and we have our final reference line for height. So this is what we mean by h initial. But notice in drawing that line, I've created a right triangle. Now, the length of the rope doesn't change, so the hypotenuse in this right triangle represents the length of our rope. If we say the rope was pulled back to some angle theta, in other words, theta equals 0 means the rope is in its vertical position, and if theta were to equal 90, this person would be swinging from a much larger or much higher ledge. Okay, so we have an angle theta. We've got the value of the hypotenuse of this right triangle, so the side adjacent to our angle must be L times cosine theta. But notice this whole distance itself is the length of the rope. So our initial height combined with L cosine theta has to add to equal the total length of the rope. So let's state that mathematically. H naught added with L cosine theta is equal to the overall length. So H naught is equal to L minus L cosine theta, or if we want, we can factor out the L. Say it's L times the quantity 1 minus cosine theta. Okay, so step 1 was the law of conservation of energy. Step 2 was reducing it to the forms of energy that are applicable in this problem. Step 3, we do algebra to solve for the final velocity. And in step 4, we're going to make this substitution and say V equals the square root of 2GL times the quantity 1 minus cosine theta. And there we have it. We can figure out the speed. Now let's give some values here and say, in this case, what if theta was equal to, how about 30 degrees? Then the final speed would be equal to the square root, grab your calculators, 2 times 9.8, let's include the units here, 9.8 meters per second squared, times the length of, what did we say, 6 meters, times 1 minus the cosine of 30 degrees. Okay, well, look at the units. Meters multiplied by meters per second squared will give meters squared per second squared. But we are taking the square root of all this, so the end result will be meters per second, and we are solving for velocity after all. Okay, so I get very nearly 4 meters per second. I get 3.97 meters per second. We can say that's approximately 4 meters per second in this example. Here's another interesting question. What would be the tension in the rope? Well, now we might need to know that the mass of the person is 50 kilograms. Now, what if this person were just hanging from the rope? What if they hadn't stepped off this ledge? What if the rope was always in a vertical position? How much tension would be in the rope? Well, if they're just hanging at rest, then they're in a state of equilibrium. The tension pulls up, gravity pulls down. 50 kilograms times 9.8 meters per second squared gives us 490 kilogram meters per second squared. In other words, 490 newtons. So the tension would also have to be 490 newtons. But the person isn't at rest when they reach the bottom point. They're in motion, and they're in motion through a circular path, which means there must be some centripetal acceleration. There has to be a net amount of force pointing toward the center of the circle. And so we have an incorrect free body diagram. The tension would actually have to be greater than mg. So that this vector that points up should be drawn even longer than the vector that represents the force of gravity. If that's the case, then there's a net amount of force that points up, and it would simply be equal to the tension minus the force of gravity. Because this is a centripetal force, then we say m times centripetal acceleration is equal to t minus mg. So m times v squared over r is equal to t minus mg. So if we want to find how much tension, it's mg plus mv squared over r. Okay. By the way, there's no distinction in this case between the radius of the circle or the length of the rope. So if we want, we can scribble out the r and replace it with L. So step 1 is a statement of Newton's laws. Steps 2 and 3 involve some substitution and rearranging. Now in step 5, we're going to make a substitution. We can substitute something for v squared. After all, we solved for v in our previous work. So v squared would be everything under the radical sign. 2gl times the quantity 1 minus cosine theta. I guess I could write square root and then square all of that, but no point in that, right? Well, notice here that the L cancels out of the equation this time. And now we can factor out mg. T equals mg times the quantity 1 plus, see we've got an m and a g, so 1 plus 2 minus 2 cosine theta, if we distribute this 2, yeah? Well, 1 plus 2 is, of course, 3. Well, how about that? Curious to see what shows up in the comment sections of the video after that brilliant statement. T equals mg times the quantity 3 minus 2 cosine theta. There we go. So in this example problem, the tension as this person goes through the low point in the swing would be 50 kilograms times 9.8 meters per second squared times 3 minus 2 times the cosine of 30 degrees. Okay, let's see what we get. So we get 490 newtons times 1.268. Which equals 621 newtons. Or another way to think of it is the tension would be about 127% of the person's typical weight. We could ask this question in reverse. Say, what would the angle have to be so that the person feels a tension twice as great as their weight? It's kind of difficult just to hang from a rope, right? If you want to suspend yourself from a rope, you have to be pretty strong because at the very least you have to support your body weight. But if you were to swing through a rope that was pulled back an angle of 30 degrees, you have to be strong enough to hold more than your body weight. You have to be strong enough to hold 127% of your body weight. So the question we're asking now is, how big would this angle have to be so that somebody who's strong enough to hold 2 times their weight would just barely be able to hold on as they swing through the low point? So T equals mg times 3 minus 2 cosine theta. That's our result. And we're suggesting here that the tension would be equal to 2 mg. So 2 mg equals mg times 3 minus 2 cosine theta. We can cancel out the mg. So this means 2 cosine theta is equal to 3 minus 2, or in other words, cosine theta is equal to 1/2. So theta would be equal to 60 degrees, right? Yeah. If you were to swing on a rope swing, pulled back at an angle of 30 degrees, you have to be strong enough to hold 127% of your body weight. If you increase that angle up to 60 degrees, now you have to be strong enough to support twice your body weight. What would happen if you were to swing on a rope starting at 90 degrees? If I'm not mistaken, there's a ride at Magic Mountain, if you've ever been there. It's not included with your entrance fee. You have to pay an extra amount of money, and they strap you in. I think you can ride with as many as 2 other friends, and you and your friends are suspended by a harness, hanging with your body horizontally, and then a winch pulls you up so that you end up very nearly at an angle of 90 degrees when released. And so your speed as you swing through the low point is rather large, and fortunately you don't have to use your arms to hang onto the rope. You're strapped in with this harness. Well, if the angle really was 90 degrees, then let's see. T is equal to mg times 3 minus 2 cosine theta. But the cosine of 90 degrees is 0. So the tension would be 3 times your body weight. Okay, so 60 degrees, 200% of your weight. 30 degrees, 127% of your weight. And if you're to swing from a horizontal rope, then 300% of your body weight. Interesting. Hey, how high does this person expect to swing when they reach the other side of the swing, right? Well, because of the law of conservation of energy, the kinetic energy here equals 0, but the potential energy is at a maximum value. As they swing through the low point, now the gravitational potential energy is 0, provided we're setting the low point in the swing as our reference level, and now the kinetic energy is a maximum. Really what's happened is we've just traded gravitational for potential. So if that's the case, they should swing to the other side the exact same angle that they had released from and reach the same height again. And then as they swing back, they'll have the same speed at the low point on the return swing as they did on the forward swing. And ultimately, if there's no conversion of good, useful mechanical energy into wasted thermal energy in this process, then they'll return to the exact same height where they had stepped off the ledge. Of course, there's some air resistance here, so in fact, they probably return to a height that's just a little bit lower. There's a famous demonstration of this. Any physics teacher worth his salt will stand in front of his students with his back against the wall and hold a bowling ball to his chin. Release the bowling ball, close his eyes, and have faith in the laws of physics that the bowling ball, although it gains a lot of speed through the low point in the swing, will swing to the same height on the opposite side, so when it returns, it can go no higher than where it was released from. So I'll link a video to Professor Lewin from, I believe, MIT, demonstrating this one with a very large, long rope and a bowling ball, and then I'll record myself doing the same one with a slightly shorter rope. Anyway, for now, thanks for watching.